We'll start by looking at direct proofs. Recall that a theorem is usually saying that there is some hypothesis, and if these hypotheses are true, then the conclusion is true. A proof then is a sequence of statements that starts at the hypothesis and reaches a conclusion through logically valid arguments. And that's how a proof is written, but that's not how it's discovered. The discovery of proof is completely nonlinear and cannot be described or cannot be compartmentalized. So we'll start with direct proof. What is a direct proof? Direct proof is the simplest form of proof. It's just a sequence, a series of implications. So you will start with the hypothesis, whatever is given in the theorem as it is. Then from this hypothesis, you will say that the hypothesis implies something, let's say P. Then you will say P implies Q, and Q implies R, and so on. So you will have a direct sequence of implications until you reach the conclusion. We are just talking about the writing of the proof, not the discovery of the proof. The discovery of the proof is still highly nonlinear. So let me do one easy example and one complicated. So the easy example I want to start with is, let's do sum of two rational numbers is rational. So now we are going to actually do the whole proof in all the detail. Now, before you start writing the proof, you have to discover the proof. You have to figure out what the proof is. You usually do this as scratch work. Here, you're not trying to be completely accurate, but you are still trying to be logically accurate. Even if it's scratch work, you still have to do things a little systematically. You have to keep track of what your hypotheses are and what your conclusion is. So I'll make two columns. Here's my hypothesis, and here's my conclusion. Okay, so now I want to say sum of two rational numbers. Let's say you have variables x and y, where x and y are rational numbers. Now, what does it mean for x and y to be rational? X is a ratio of two integers, and y is a ratio of two integers, and the denominators are non-zero. But this is scratch work, so I'll leave it like this. And the conclusion I want to get to is that x plus y is also rational. So I want this to be something like a or b. The proof is going to go from here to here. You should always keep track of what your hypothesis and what your conclusion is. It is such a common mistake to confuse the conclusion with the hypothesis. And it's not a hard thing to do. You just write everything down. To be very deliberate with your writing. This one, there is not that much to do. You can do x plus y. Starting from the hypothesis is PS plus RQ over QS. And that looks like A over B. So it looks like I have a proof, and the proof is literally to add things up. Okay, so that looks promising. So let me start. So that was the discovery of the proof. The discovery can be in any order possible, but when I write the proof, I must start with the hypothesis. My hypothesis is I'm starting with two rational numbers. So I'll say let x and y be rational numbers. Now I need to expand on what a rational number means. So this will change into that x be equals to p over q, y equals to r over s, where p, q, r, s are integers, and q is non-zero, and s is non-zero. When you write proofs, you write full statements, and you state all your assumptions in advance, and you declare all your variables. So for example, x and y, I'm saying they are rational numbers, so I'm declaring their domain. Then p, q, r, s, I'm saying they are integers, so I'm telling you what they are. Then my assumption is that q is not zero and s is not zero, so I'm also putting that in there. All of these are not optional. You have to write proofs in all the detail possible. Then x plus y is p over q plus r over s is qs times. Another thing, you should never have two equal signs in the same line. If you have an equation with multiple equal signs, this is how you write them, one below the other. And now here, ps plus qr and qs are integers and QS is not equal to 0. So what I've done is I'm expressing x plus y as ratio of two integers whose denominator is non-zero. And hence I can conclude that x plus y is a rational number. So this is how you would write a proof. Now let me do a complicated example. So you're trying to show that every multiple of 4 can be expressed as difference of squares of two integers. So I'll start with the hypothesis. The hypothesis says that every multiple of 4. So let's start with a number that is a multiple of 4. And the conclusion is that it can be written as difference of squares of two integers. So the conclusion is saying that x is equal to a square minus b square, where a and b are integers. What can you do? How can you start with something that is 4k and get something that is a square minus b square? I don't know. So we play around with something. The right-hand side, sorry, the conclusion looks like something which can be simplified. So I can express this as a minus b plus b. Now, how can I go from 4k to that? And the real answer is try things out, guess, and maybe you can find the solution. Okay, so let's try guessing. One guess can be 4 is a minus b and k is a plus b. That looks promising. I'm trying to find a and b. I'll add the two equations together. 4 plus k is equal to 2a, which gives me a is equal to 4 plus k divided by 2. So this gives me a, but there's this problem here. I want two integers, and I have no guarantee that 4 plus k over 2 is an integer. For example, k can be odd. So it's a good idea, but unfortunately, I'm stuck at this point. Okay, so it doesn't work. What can I try else? So this was the place where I tried something. That just means I need to try something else. So I can try 2 equals a minus b and 2k equals a plus b. And I add the two together and I get 2 plus 2k is equal to 2a. And then I divide by 2 and I get a is equal to k plus 1 or 1 plus k. Well, this is excellent because k is an integer and so 1 plus k is an integer. So I got an a. We're not done yet. I still need to figure out if I can get a b. How can I get a b? I can use the first equation. So I'll get 2 is equal to 1 plus k minus b. I'll transfer b on the other side and 2 on that side. That will give me k minus 1. Excellent. So it looks like k plus 1 and k minus 1 are the things I'm looking for. The next step I should do is this is scratch work, that's why I'm being messy, and this is how mathematicians usually do it. They're a little messy when they're trying to discover proofs. I should try to expand a square minus b square. So I can do k plus 1 square minus k minus 1 square. And I'll let you work this out, that this actually is in fact 4k. And great, so now we have our a and b, we have our candidates, and we can start the proof. Notice that discovery of proof was a complete mess, but now I'm going to write the proof, and the writing of the proof will be very systematic and linear and elegant. Okay, so start with the hypothesis. The hypothesis says that we are looking at multiples of 4. So let x be a multiple of 4. This is like saying that x be equal to 4k, where k is an integer. We want to show that x is equal to a square minus b square for some a and b integers. And I'll just come up with them by using the scratch work that I did above. Let a be equal to k plus 1 and b be equal to k minus 1, then a square minus b square is equal to k plus 1 square minus k minus 1 square, which is equal to k square plus 2k plus 1 minus k square minus 2k plus 1. K square cancels with k square, 1 cancels with 1, and I get 2k plus 2k, that is 4k. But 4k is exactly x. And so I've shown that a square minus b square is equal to x. This is what we were supposed to prove. Notice the difference between the writing of the proof and the discovering of the proof. And this is an example of a direct proof because every statement just follows from the previous statement.